Hello, everyone. Today we'll be going through artificial intelligence topic presentation. So my team is Group21. It consists of Monica, Shumaila, and myself, Vandana. So let's go ahead and look at what are the topics that we'll be talking about. So we have two different articles that we are going to talk. So the first one will be mastering the game of Go with deep neural networks and research. And the second one we'll be talking about is the mastering the game of Go without human knowledge. So let's go and start with the first paper. So these are some of the topics we'll be covering in the first paper. So supervised learning, reinforced learning, on the policy networks and the value networks, and then evaluating the strength of AlphaGo, and finally the conclusion. So the introduction. So as we know, Go has they have been trying to implement games into AI through AI, and Go has been proven to be a difficult game to incorporate in an AI because it has a large search space, as well as it's difficult to evaluate the board moves and the positions. As these are some of the problems. So to accomplish to overcome these problems, what we have done is they came up with a new approach where it involved a value network, which was used to evaluate the board moves, and a policy network to decide the moves, which move to take. And then in this particular article, what we'll be going through is we'll combine the Monte Carlo tree search algorithm with the value and policy network to come up with a solution. So this method, using this method, we can defeat a human, we have defeated, or let's say they have defeated a human European Go champion and attained a 99.8% winning rate against other Go players or games. So what exactly is it? So let's go in depth into the concepts that we just discussed. So that is, so for the traditional method, in the traditional method, we have the optimal value function that is represented by V star of S, which is used to determine the game's outcome, where S denotes the current state of the board. So this is found out using a search tree, where with B to the power D representing the possible move sequences, where B is the number of moves per position and D represents the length of the game or the depth. So in chess, usually it takes around the number of moves is 35 and the depth of the game is 80. But when we go into Go, it takes 250 positions or moves, number of moves per position, and around 150 is the depth of the game. So this kind of search is very infeasible. So to overcome this, we have two different ideas. So the first one is to minimize the depth of the tree by evaluating its position. So this is done by we truncate the tree at a particular state S, and then replace that the tree or the subtree below S with a value function, which is V of S, which is equivalent to V star of S. That is our optimal value function. So that returns the S state S's result. So we were able to this particular approach, they were able to solve the chess, checkers, and Othello, but not Go. So the second idea was to narrow the search by selecting the actions from policy, P A of S, where A is the number of actions and S is the state. So which is the probability distribution for overall possible moves in position S. So what we do is we perform a simulation. So this is the traditional method. So what is exactly Monte Carlo tree search? So here what we do is we perform the simulation on the Go system in the Monte Carlo tree search. So as time passes, the system, what it does is it trains the model so that the model finally gives us the optimal play and optimal value function. So they could get to the by using this Monte Carlo tree search, they could achieve amateur play level in Go. So to go more to achieve a higher rate, so we use deep convolution neural networks. So it was utilized to generate outstanding results in visual domains such as face recognition, image classification, and gameplay. So what they did is they constructed a progressive abstract, localized the representations of images using multiple layers of neurons, each arranged in overlap tiles. So in Go, what we do is we apply the same principle. So we take the whole Go board as a 19x19 image. So we use these neural networks to minimize the search tree's effective depth and breadth. So a value function here or a value network here evaluates the places, and a policy network gives us the sample actions. So what we do is here in this method, we initially use the supervised learning to train the neural networks, which gives us a quick and immediate learning updates based on the given feedback. Then following that, we'll do a reinforcement learning, and which improves this supervised learning to get to a best possible end result. So next is to train the value network that forecasted the reinforcement learning policies winning games. So in this way, the Monte Carlo tree search was combined with the policy and value network. So as you can see here in the rollout policy, we can from the supervised learning, we train the model, and from there that is given as an input or to the reinforcement learning, where it is again trained through self-play, and then it goes from and then based on that we are predicting the actual outcome, which is the best outcome in the value network. So next is, let's go in depth regarding the supervised learning of policy networks. So what they have done is they have recorded a collection of expert actions for a specific state, so which is used to train the system to get to the current state. So the current state is the of the policy making is defined as the transition from the action A to S. As you can see, transition from action A to S. So we use the KGS Go server's 30 million positions as the data set for the supervised learning policy network. So from here, if it's a large network that has, then we have an accuracy of over 57% of the input features, but we'll get it, the evaluation is slow, and it takes around 3 milliseconds. Whereas we have a faster but less accurate rollout policy. So that is achieved by only giving a small set of features, which has given us an accuracy of around 24.2%, and it takes around 2 microseconds to do that. So this is the algorithm or the function that they use to calculate this, calculate the accuracy. And as you can see, as and when the if we take the data sets based on the data set taken, we see the graph here for the KGS data set against the AlphaGo win rates. Next, let's look at the reinforcement learning of policy networks. So reinforcement learning is it's similar to the supervised learning network, but the weight here is P instead of the lambda or what we had, but it's the same. So the weight is the same. So the outcome for this, the outcome for the game is represented by Z of T, which is in turn a function of R S of T. That's where we get the reward. So R is the reward, S is the state, and T is each step. So if at all it's a winning game, then the Z of T value will be +1. If it's a losing game, then it will be a -1. So based on that value, we'll be able to give the proportional details for the policy network. So once this policy network has been trained, it will win more than around 80% of games against supervised learning policy networks. So it has won more than 85% games against Pachi that uses 100K Monte Carlo simulations per move. But in previous, like the state of art supervised learning, they like learning on a conventional network, it won against 100% games against Pachi and 12% against, sorry, 11% against Pachi and 12% against a weaker program called Fugo. So next we'll be learning about the reinforcement of value network. So this is the final stage of the training where we predict the winning probability of the policy. So the naive approach of predicting the outcome of KGS data set is that the outcomes are strongly correlated and overfitting. So we achieve around 0.37 MSEs on the test set, and when compared to that of the training set where we have the 0.19 MSEs as the system's outcome system, as the system memorizes the game's outcome, then finding what it does is it just memorizes the outcome. So we reach the outcome. So this is how we reach the outcome. So it doesn't like use a new position or it doesn't go to like check other positions so that we could get a better result. So to overcome this particular issue, a new idea where a self-play data set of like 30 million different positions, like each sampled from different games were generated. And this resulted in like a much less overfitting, which was around 0.226 MSEs on a training set and 0.234 MSEs on the test set. So that there was a very little gap there. So this approach was ideal. So, and the function used to calculate this value is given here. And then we have the searching with policy and value networks. So the four neural networks, there are four neural networks that is used in the AlphaGo game. So three policy networks such as rollout networks, which has, even though it has less accuracy, but faster inference, which is useful in the context of Monte Carlo tree search. So supervised learning is then the second one where the policy network is trained. And then we have the self-play reinforcement learning. And then the fourth neural network, that is the value estimator that predicts the actual value of the state. So that is at the end of the particular game or the episode. So it is predicting what it does is it's predicting the winning probability for a given state. So Monte Carlo tree search is like it ties all together to form the like all these four policies, four neural networks and the policies together to like form the AlphaGo agent. So it consists of four set of pipelines, that is the selection, the expansion, the evaluation, and the backup. So in the selection, what we do is we start with the given state and then say some configurations of the Go board or some configurations of the chess board and simulate different actions it can take and simulate action opponents might take in order to like form that particular tree. So whatever actions we are taking, whatever actions the opponents are taking, so that simulation is done. And each edge of the tree has a weight to it. So we take the branch that has the max and reach all the way down to the leaf node. Now, then what we do is we expand the leaf node. We use the policy network gradient of supervised learning and to expand the node. And then because we use this approach because the supervised learning approach, because the humans have like selected a vast network of moves when compared to that of the agents. So once the leaf is expanded, they construct a new node and they use the rollout policy to simulate all the way to the end of the tree or the game or the episode. And then they get to the point or the win node that is a combination of the Q, that is Q plus U of P that we have here of that particular new node that we had previously constructed. And then at each step for a given time of each simulation, an action A of T is selected from state ST and AT. So is the AT is the probability proportions, and N of S of A is the visit count, and Q S of A is the action value, and V S of L is the value function. So these are all the formulas that we are using for that. So next slide, we have more on this. So as the AlphaGo employs and like asynchronous multi-thread search that runs simulations on the CPUs, while simulation simultaneously what it does, it computes policies and value networks on the GPUs. So, excuse me, AlphaGo uses like 40 such threads, where 48 CPUs and 8 GPUs. Whereas in a distributed AlphaGo, it uses like 40 search threads, and 1,202 CPUs and 176 GPUs. So to achieve the whatever model we were talking about before, this is what is the requirement for AlphaGo and distributed AlphaGo. And then let's go into the evaluation of the playing strength of AlphaGo. So after like several AlphaGo variants and Go programs, such as the Crazy Stone, Zen, Pachi, Fugo, and GunGo. So the results show that the AlphaGo has a stronger rank when compared to the other previous Go programs. So that is around 99.8% of it. So in a, let's say, there's a handicap game. We call this a handicap game because the opponent is given free moves. So even on that, AlphaGo has won 77% of the games against Crazy Stone, and 86% of the games against Zen, and 99% against Pachi. So in, let's say, so that's in the single machine. So as you can see in the last, we have a distributed machine as well. So using the distributed version of AlphaGo, we have won around 77% of against the single machine AlphaGo, and 100% against all other programs. Then we have a variant of AlphaGo such as a value network or just a rollout, where which were also assessed. So without rollouts, also AlphaGo had the highest winning performance when compared to other programs. When a mixed evaluation is performed, AlphaGo had a winning probability which is greater than or equal to 95%. This means that the value network, it provides approximately the outcome. The same approximates, like it approximates the outcome, but it is slow. But in the rollout, we can score, we can have a score and we can evaluate the outcome correctly, but yet fast rollout, it has a weak, it's weak, that outcome is weak, but it's faster, we get the outcome faster. So finally, we are here looking on the conclusion. So a system that that provides that effective moves and positions, evaluate like using neural networks, are trained using the supervised learning and the reinforcement learning. And using that machine, they have defeated Go champion Fan Hui in 5 different games and won all the 5 games. So what it does is it used lesser moves than Deep Blue by selecting the positions intelligently using the policy networks and evaluating using the value networks. So this is what it did here was it the system was thinking similar to how a human would play the game. So AlphaGo was like trained directly from gameplay through like supervised and reinforced learning. So some of the previously designed Go programs and the Monte Carlo tree search have also been used like in different areas other than the Go game. They have been used in normal games. They're like used in planning, partial planning, scheduling, and constraint satisfactions. Also, like by combining the policy and the value network with the tree search, AlphaGo has like reached a professional level in Go. So proving that like human level intelligence can be achieved in other UI domains as well. So That is it from my end. So my teammates will continue from here.
Hello everyone, my name is Monica Madineni, and I would like to tell you about the methods of mastering the game of Go with deep neural networks and the tree search. First of all, coming to problem setting, the optimal policy for two-player games is determined by a probability distribution, our legal actions, in a state space and given random input. The optimal value function is expected outcome for both players if both actions are selected according to the optimal policy. Coming to prior work, we can use depth first search to find the optimum value function of a game, but it is not effective in Go. Reinforcement learning has been used to learn the optimal value function in a number of games and to train neural networks to approximate the optimal level function. A more accurate approach to minimum search is Monte Carlo tree search, which uses a simulation policy with a bonus to encourage exploration or samples action from a fast rollout policy and convergence to optimal value function. The previous work has combined Monte Carlo tree search with a policy that narrows the beam of the search tree to high probability moves or biases the bonuses term towards high probability moves. The performance of Monte Carlo research is strongly independent on the quality of the rollout policy. AlphaGo uses simple rollouts and evaluates its position using value networks. Next slide. Search algorithm. A simulation of a PVMC Monte Carlo tree search algorithm is performed in 4 stages, starting from the root of the tree and ending at the leaf, to select an action according to the statistics in search tree. The search control strategy prefers actions with high prior probability and low visit count, but asymptotically prefers actions with high action value. A backward pass is initiated when a leaf position is completed. When the visit count of the state exceeds a threshold, the successor state is added to the search tree and the policy network computes the probability of moving to that state. The Monte Carlo search algorithm is distributed search algorithm that uses a single master machine that executes the main search, many remote worker CPUs that execute asynchronous rollouts, and many remote workers general processing units that evaluate the policy and value networks. AlphaGo selects the action with maximum visit count. During this match, it extends a search tree and continues searching during the opponent's move. Coming to rollout policy, AlphaGo doesn't use the common heuristic of all moves as first, rapid action value estimation, and dynamic combing. Instead, it uses rollout policy using local pattern based features, a linear softmax policy, and small handicrafted local features to maximize log likelihood of the final position. And policy network. We used a policy gradient update to determine the outcome from each player's perspective. Next slide. Value network. We trained a policy network from a dataset of over 30 million positions and use a value network to approximate the value function of the SL policy network. We used a new data set of uncorrelated self-play positions and trained a policy network for 10,000 mini batches of 128 games. Features of policy network or value network. We trained a policy network from a data set over 30 million position and used a value network to approximate the value function of the SL policy network. The value network is trained on the set of features planes that come from the raw representation of the Go game rules, indicating the status of each intersection of the Go board, like stone color liberates, captures, legality turns, since stone was played and the current color is to play. Coming to neural network architecture, to train AlphaGo, we first pad the input image into image stack, then apply a rectifier on non-linearity and K filters of kernel size with stride 1. In the value network, the input is image stack with an additional binary feature plane. The output is fully connected linear layer with 256 rectifier units and a single TAN unit. AlphaGo played against existing Go gamers with a handicap of with a handicap. This is equivalent to giving one extra free move to black instead of giving free move to black using standard non-comic handicap rules. Each computer Go program was ranked based on the highest KGS ranking it achieved. Fan Hue was arbitrated by the impartial referee, and the overall match outcome was determined solely by formed games, AlphaGo was respectively. The remaining part will be continued by Shumaila.
Hello everyone, my name is Shumaila Sefi, and today's topic is mastering the game Go without human knowledge. So, Vandana, next slide, please. Okay, so we have different topics here. We are going to explain first the introduction part, reinforcement learning in AlphaGo 0, comparison of network architectures for policy network and value network, and empirical analysis, knowledge gained by AlphaGo 0, and finally the conclusion. So next slide, please. AlphaGo 0 without is a algorithm that is completely based on reinforcement learning with no human supervision or domain expertise, just the game rules. So this algorithm is without the human intervention. AlphaGo becomes its own teacher with a neural network trained to forecast AlphaGo's own moves, selections, as well as the outcome of its games. The strength of the tree search is improved by the neural network, resulting in greater quality, move selection, and stronger self-play in the following iterations. Next slide, please. Reinforcement learning in AlphaGo 0. So it uses a deep neural network F theta with parameter theta. So theta is a parameter. Next slide, please. We can understand the reinforcement learning in AlphaGo 0 with the help of this neural network figure. So there are two figures. In first figure, we can see the program competes against itself in the games S1, S2, and up to ST. In each position, S1, alpha theta is executed using the latest neural network theta. To compute the game winner Z, the terminal position ST is scored according to the game regulations. In figure B, neural network training. So the neural network takes the raw board position ST as input and runs it through a series of convolutional layers with parameters and outputs a vector PT that represents a probability distribution over moves as well as a scalar value VT that represents the probability of the current player winning in position ST. The neural network parameters are adjusted to maximize the policy vector PT's similarity to the search probabilities T and to minimize the difference between the predicted winner VT and the game winner Z. Next slide, please. Yeah. Empirical analysis of AlphaGo 0 training. So here there are 4 neural networks in the figure is presented. So we will go through one by one. So in the first figure, each simulation traverses the tree by selecting the edge with the highest action value Q as well as an upper confidence bound U based on a prior probability P and visit count N. Count N is incremented once traversed. So in the second part, B part, the neural network expands the leaf node, evaluates the associated location S, and stores the vector of P values in the outgoing edges from S. And in the third one, just a moment. The mean of all evaluations V in the subtree below that action is tracked by the action value Q. good activities eventually have a higher N than bad actions. And in the last one, D part of figure. So D neural network, at the end of the search, an action A is to be selected to play the root position S with probability pi. Next slide, please, Mandra. It's empirical evaluation of AlphaGo 0. So here there are three graph representation. So in AlphaGo 0 had outperformed AlphaGo Lee in after 36 hours. Although supervised learning from human data using the same architecture performed better at predicting human professional moves. It can be seen in figure B. The self-trained player still outperformed the human-trained player in the first 24 hours. And AlphaGo 0 may be learning a strategy that is qualitatively distinct from human play according to the results of the experiments. Vandana, next slide, please. Okay, so here the comparison of network architectures for policy network and value network. So in this comparison, first of all, what the values are, that is dual res, sep res, dual con and sep con. So dual res is single network with residual blocks. Sep res is separate network with residual block, and dual conv is a single CNN, and the sep conv is two separate CNNs. So in this figure, to find a different player, each trained network was coupled with AlphaGo 0 search. And for each network design, the precision of human professional moves is predicted. For each network architecture, the MSE of human professional game outcomes. On the next slide, please. Now, this is the final performance by the AlphaGo 0, and it can be understood by these two figures, A and B. And first one is the graph, and the second one is another graph. So in the first one, the AlphaGo 0's learning curve over 40 days using a larger 40-block residual network. The graph depicts that each player's performance in each iteration of the reinforcement learning algorithm. And in the second graph, in the final performance of AlphaGo 0, a 40-block residual neural network was used to train AlphaGo 0 for 40 days. So AlphaGo 0, AlphaGo Master, and AlphaGo Master, who defeated top human pros from 60 to 0 in online games, and AlphaGo Lee, who defeated Lee Sedol, and AlphaGo Fan, who defeated Fan Hui. And prior Go programs, Crazy Stone, Pachi, and New Go are all shown in the graph. So this is the performance measurement of the AlphaGo 0 algorithms. Next slide, please. Knowledge learned by AlphaGo 0. So whatever we learn, it is basically a larger neural network and a longer time to apply a reinforcement learning process to a second instance of AlphaGo 0. The training began with random behavior and lasted roughly 40 days. So over the course of the training, around 29 million self-play games were created. Next slide, please. The conclusion part is here. So to conclude, AlphaGo 0 was able to recall most of the Go knowledge as well as creative techniques that bring new insights into the oldest of games after starting from scratch. A new reinforcement learning method is described, which results in state-of-the-art performance for demanding situations and is motivated by the dual process theory of human mind. From here, Monica will continue. Monica.
Coming to the methods of mastering the game of Go without human knowledge. Reinforcement learning. Reinforcement learning is used to generate a sequence of improving policies by alternating between policy evaluation and policy improvement. There are several approaches to policy evaluation and policy improvement, including classification-based reinforcement learning and classification-based modified policy iteration. The AlphaGo Zero self-play algorithm is a policy iteration scheme using multi-class research for both policy improvement and policy evaluation. Policy evaluation is applied to a search policy and outcome of self-play games are projected back into the function space of the neural network. Self-play reinforcement learning in games. Previous work has been applied to self-play reinforcement learning, the game of Go. The NeuroGo used a neural network and ReGo used a linear combination of features to predict the winner. Monte Carlo search tree is a form of self-play reinforcement learning that uses the nodes in the search tree to predict the winners of simulated games of self-play. The self-play reinforcement learning approaches that achieved high levels of performance in other games, but these methods use pre-existing computer programs as training opponents or a part of learning process. Many of the most successful methods for learning were first introduced in the context of zero-sum games and have since become widely used in video games, robotics, industrial control, and online recommendation systems. Next slide. AlphaGo versions. The program that defeated Lee Sedol 4-1 used different neural networks, was trained for more iterations, and was distributed over 48 TPUs rather than GPUs. To evaluate neural network faster during search. AlphaGo Master uses the same neural network architecture as AlphaGo Lee, but was initially trained by supervised learning from human data. AlphaGo Zero learns from self-play reinforcement learning, starting from random initial weights without using rollouts or human supervision. The raw board history as input reference. It does not need to know domain knowledge. Coming to domain knowledge, AlphaGo Zero is provided with a set of legal moves in every position and can play any game that reaches a terminal state. AlphaGo Zero exploits the fact that the rules of Go are invariant to rotation, reflection, and color transportation, and this represents the board from the perspective of the current player. AlphaGo Zero does not use any form of domain knowledge beyond the points listed above, but only its deep neural network to evaluate leaf nodes and select moves. AlphaGo Zero neural network architecture is based on current state of the art of an image recognition, and hyperparameters are chosen to optimize self-play performance of AlphaGo Zero using the neural network trained in a preliminary run. Next slide. Coming to optimization. To improve the quality of data, a neural network is optimizing using TensorFlow on the Google Cloud. The neural network is evaluated against the current-based network, and if the neural network performs better, is used to generate more self-play data. Evaluator. The best player is chosen by playing 400 games using a search that uses the leaf positions and prior possibilities. If the player wins, it becomes a baseline. Self-play. The best current player is used to generate data, which is then used to train the neural network. The neural network is trained to play games by selecting moves proportionally to visit counts in MTS, with a temperature of 1 for the first 30 moves. Supervised learning. The combined policy and the value network architecture are low weight of the value component made it possible to avoid overfitting to values and improve move prediction accuracy and value prediction error. This algorithm begins with search tree, iterates through 3 phases, select one move, and then plays the game according to the statistics of search tree. Next slide. Coming to neural network architecture, AlphaGo Zero does not use any rollouts using single network instead of separate policy and value networks. Leaves are always expanded. There is no tree policy, and the transportation table is used in the large instance. In our study, 4 different neural network architecture were compared, 3 supervised policy networks and 2 unsupervised networks, resulting in a depth of 39 or 79, respectively. Neural network architecture comparison. For supervised learning, networks were trained on a fixed dataset of 2 million games of self-play data, and their strength was evaluated by measuring the ELO rating of each player. AlphaGo 0 was tested against Go players in Soil and Go Kifu dataset and the KGS dataset. By this, we are going to conclude our presentation. Thank you.